You're all journalists, and I want to start with something that is quite important from those of us who work on research in health. When I was getting my master's in public health, we spent a lot of time in all of our classes talking about what is causation. And it's important today because when we look at global environmental change in health, there's so much interest in the field, which is really excellent. There's lots of researchers coming into the field, which is desperately needed. But there is not a lot of due diligence being done by some. And so the field is full of studies that are full of correlations. I have a data set, I'm going to correlate it with ambient temperature. It doesn't meet the basic Bradford Hill criteria that were put out in 1965 on how to decide whether something's a correlation or a causation. I'm not going to go through these, but it's good to know that these criteria exist, but they're not being applied very much at the moment. And if you've got questions about any aspects of these, I'm happy to cover those. But just to know that there are standards that should be followed in health studies to help you, when you report, understand when there is causation and when there isn't. All right, I'm going to keep trying. One day this is going to work. Within the field of climate change, there are sophisticated statistical methods for determining causation. This is not, it's just starting to be applied on the health side. I'll talk about that in a moment. But on the climate side, there is a whole field called detection and attribution. And detection and attribution does exactly what the name implies. It detects whether there's a change in a trend. If there has been a change in a trend, then again, sophisticated statistical analyses determine how much of that change in a trend is because of climate change itself. And this has been used since the second assessment report by the Intergovernmental Panel on Climate Change. The last assessment report, there was a whole chapter on this in the Working Group 1 report. So these are very well developed methods. And they're just starting to be applied to health. It's critically important, in my perspective, that this field be advanced because it's changing the discussions around climate change and health. I'll use the Pacific Heat Dome as an example. This was about a 4-day event a couple of years ago. It was, first of all, it was accurately forecast. Nobody believed the forecast because the weather was forecast to be so extreme. You can see how much records were broken by. For people who follow your local broadcast meteorologist, typically records are broken by tenths of degrees. We had records broken by 10 degrees. That hadn't happened before. It was so extreme. The city was not prepared. I'll speak for Seattle-King County. The city was not prepared. Again, they didn't believe the forecast. There's not a, at that point in time, was not an early warning system. The city scrambled. They really tried to do everything they could to help protect people from these extremely high temperatures. As I'll mention later, another critical component, it was really hot at night. If those nighttime temperatures had been the daytime highs, even those would have been records. So people couldn't cool down at night. When the data finally came in, because it takes a long time to get the health data in the state of Washington, there was over 440 excess deaths from this event over just a couple of days. There was a rapid detection and attribution study on the event that said this event was virtually impossible without climate change. And so this event means that myself, my colleagues can stand up and say those people died from climate change. This is not that there's associations between heat and mortality. These are people who are dying from climate change. And that changes the discussion. It changes the dynamic with ministries and departments of health because this squarely falls into their mandate. The other point I'd like to make on this is that heat is an all of society issue. And so when thinking about these issues in health, I will talk about hospitalizations, I'll talk about mortality, but it's more than that. This event occurred at the height of our cherry picking season, lost a big fraction of the cherry crop. We're one of now 5 states in the US that has regulations to protect outdoor workers. Those came into force to protect the workers. I remember watching the media that one of our orchards, as part of the process with bringing in the cherries, there's a large walk-in chiller, basically. And they had all of their workers spend time there to help get that core body temperature back down. The other is between south of Seattle and up to Vancouver, BC, is an area called the Salish Sea. The estimate is that during low tide, the water temperatures were so high that about 1 million mussels, clams, and oysters were literally cooked. That's food security. That's economic security for some of the sovereign nations that line the Salish Sea. And so thinking more broadly about these kinds of impacts can help enrich your reporting. There's quite a bit going on in the field of detection attribution. This is a study that came out a couple of years ago that looked at 43 countries, over 700 locations in these countries, and looked at about 20 years for each country of data of mortality associated with heat. So looking at the correlations, but then matching this with some work that's been done in the climate science on detection and attribution, and then was able to produce this, which shows that across these 43 countries, about 37% of all heat-related mortality is because of climate change. The numbers are large. There's a couple of papers came out the last 2 years from a group in Barcelona looking at mortality, heat-related mortality in Europe. Estimated in the summer of 2022, there was more than 60,000 Europeans that died from the heat. The following summer, it was about 47,000, if I remember correctly. But if you say about 40% of that is due to climate change, these are large numbers. You can see there's variability across these countries. If you can read it, you can see there's just one country for all of Africa. So there's a lot of work that needs to be done, and it's an important start. One other thing I wanted to make you aware of while I'm talking about detection and attribution, how many of you know Climate Central? Great. How many of you know the Climate Shift Index? A few of you do. So it's a new product from Climate Central. It produces a map every single day and shows you the temperatures around the world and how far they are away from the long-term average. So anything that is in the redder colors are all temperatures that are higher because of climate change. And so when you're looking at your reporting, you can use this to see the temperatures in that place and whether they're normal or they're outside the range of normal. And these go back to about 1980. They've got a big database. With that, I was going to move on, but I wanted to start with that as a background because that underlies much of what I'm going to say. How many of you have seen this figure? So a few of you have seen this figure. Every Intergovernmental Panel on Climate Change assessment cycle ends with a synthesis report. There's always a figure in the synthesis report that shows you how much global mean surface temperature has shifted over pre-industrial times, and then projections out into the future, typically 2100, under 4 or 5 different scenarios of emissions of greenhouse gases. All of these have been figures that are line graphs. This is the first time that the warming stripes were used. I assume you've all seen the warming stripes. Yeah. So this is the first time those were used in the IPCC report, and it's the very first time they put people on the report. And this is where the title of the talk comes from. This just goes back to 1900 and just shows you the very large differences in experiences. Yeah, can I get a handheld mic if you're having trouble hearing me? Thanks. If you turn that off so then it doesn't squeal, would be amazing. Yes. Thank you. And so it shows you that depending on when you're born, how different the experiences are going to be. And this continues to be the most downloaded figure from the synthesis report and from the IPCC cycle. And it helps give a sense, as you're doing your reporting, of what we're experiencing today, first of all, is a mix of people who've got different life course experiences. And when we talk about heat, older adults over the age of 65 are more at risk of heat, but you can see that they've had less experience with heat. That in 20 years, 65-year-olds will have had more experience with heat. And so there's going to be different outcomes based on what we all experienced as we grew up. And so this can be a useful frame for thinking about how to describe some of the challenges and opportunities that we have. Let's see if this works. Oh, look at that. Another piece of framing that's really important is this one on the left. It's, again, from the IPCC. It says that as we're looking into the future, we're looking at risk, where risk is probability times consequence. And in IPCC, that risk is composed of three main factors. I'm going to make it four. The first are the hazards created by a changing climate. The second is the who and the what are exposed, the human systems, the natural systems that are exposed to those hazards. The third is the underlying vulnerability, and for health, I'll separate that out into susceptibility to harm and the capacity to manage. This is important because when we talk about climate change and health, it's not just the hazard. It's these interactions. And that also then goes back to the comment I made at the beginning about causality, of looking at papers that don't take into account other drivers of health outcomes. Because you need to understand that. Vulnerability varies from place to place. It varies across age. And understanding how vulnerability plays into what is observed and what you're reporting on. And thinking then also about the capacity to manage. For decades, we've been talking about how important it is to build the capacity of our health systems. Now that we've had COVID, everybody understands that. So it's a much easier discussion. On the right is one of many, 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 many figures on some of the changes that are going on with global environmental change, showing, based on this concept at the left, that these interact with a broad range of demographic, environmental, socioeconomic, and other factors. And so understanding the outcomes, you have to understand these interactions. These then play into exposure pathways that are typical in environmental health. Underneath is a short list of climate-sensitive health outcomes. And it truly is a short list. There's hundreds and hundreds of climate-sensitive health outcomes. So these are just examples. One thing that is critical to understand in the field is there's been essentially no funding from the beginning. Every scientist says we don't have enough research. I'm sensitive to that comment, but we really haven't had any funding. And so when you look at what's been done, when you ask me questions, a lot of them are we don't know. That I published several papers on this until last fall. Funding under National Institutes of Health for Climate Change and Health was running at less than 0.02% of their budget. When you look at the adaptation funds under the Framework Convention on Climate Change, the amount going to health was less than half of 1%. And so there hasn't been the research that we need right now to answer the questions that are coming up right now. It is starting to shift, which is the good news. And I've got a series of comments here. We can go through these as slow or as fast as you want, but I did say I'd talk about the life course. Pregnant women, the last 5 years it's come out that pregnant women are quite vulnerable to higher temperatures. That when pregnant women are exposed to higher temperatures, they more often have low birth weight babies. There's likely to be other adverse outcomes that are going to be understood over time. But this information is robust. What else did I put on here? Heat can be exacerbated by air quality, and so thinking about those interactions between heat and air quality. I'll talk about that again later. And a paper just came out about 6 days ago at what is known about prescription medications and how they can interact with the heat to make people less vulnerable. This just underscores the point of how many climate-sensitive health outcomes. This is one paper that looked at emergency department visits in the US for children for when the temperatures are quite high, so they're greater than the 95th percentile. And it's just a long list. The etiology for much of this hasn't been worked out. These are observational studies trying to get a better sense of what kinds of impacts are being observed. But to go back to causation, to say this is causation, we have to understand why. What are the changes that take place physiologically that result in these kinds of outcomes? And so there's more work that has to be done, and you're going to see this over time, that there's so many people coming into the field that there's going to be an explosion of literature and trying to understand then what is that you can communicate to your readers, that there's confidence that this is a robust finding. This is a framework that was just published a few days ago for studying aging, climate, and health. It's very similar to other figures in this field, showing the interactions of vulnerabilities and mechanisms for impact. Input is a little bit linked to a particular figure because the interactions are, of course, but it gives you a sense, again, of thinking through the various shifts that are taking place demographically in the context of climate change and health and how that can influence the outcomes observed. This is a quick summary of the human health chapter in the last IPCC report with the headline statement that climate change is already adversely affecting the physical health of people worldwide and the mental health of people where there are data. On the left are observations, on the right are projected risks. The light blue are the major categories that were assessed. At the point in time of this chapter, about 2/3 of the literature had been on heat, because that's one of the areas that agencies were willing to fund. But there's now, thankfully, a much broader range of literature coming out. Health is in a different situation than other sectors in terms of climate change. All the health risks of a change in climate are current problems. It's different you look at ecosystems and looking at biodiversity loss. It's very different in other sectors. And because they're all current problems somewhere, not necessarily where we're seeing them right now, it means that there is a sense of how to control them. And so we're coming from a place where, by and large, the field understands the vulnerabilities. It understands people who are at higher risk. Not that we're not going to find out more, because we will, but there's a lot of understanding already. The other point, the figure on the right is from the National Climate Assessment, just underscoring vulnerable groups, what can be done to help protect them. At the left is just a reminder, when we think about climate change and health, at the core is inequity, that the people who suffer the most are those who contributed the least. And so inequities are a constant theme throughout everything in climate change and health. I'm just going to run through a series of climate-sensitive health outcomes, make a few points, hopefully leave lots of time for questions. I'll start with billion-dollar disasters because there's been so many of them. These are just the billion-dollar disasters so far this year. I've got some statistics on the left about the billion-dollar disasters. NOAA's been tracking these since about 1980. First of all, I find it quite useful to pull this up because I pull it up and I'm immediately reminded of all kinds of disasters I'd forgotten occurred because there's so many of them. The second, from the health perspective, is these are insured losses. When you look at this, there's no heat waves listed. Heat waves kill, but that's not an insured loss, and so they're not considered. And when you look at the billion-dollar disasters, it's then undercounting the impacts of all of these disasters by not taking into account hospitalizations and premature mortality. There's increasing interest in mental health. This is a particularly well-done study from the UK from some massive flooding a decade ago. You can see the photograph. There's two things about this that make it particularly useful in understanding mental health. The first is it's unusual in health to separate out the exposure and the vulnerability, that usually those are conflated. But in this case, the author has separated out people who lived in a residence that was disrupted, so the floodwaters came to the front door but didn't go inside, versus a resident that was actually flooded, versus people who lived in a residence that was not affected at all. The other is there's 3 years of follow-up, which was really unique. For anxiety, traumatic stress disorder, and the point is, as you would expect, in year 1, there was a big increase in all groups. The prevalence declined for the next 2 years and does not go back to 0. That there's long-term mental health consequences from these very extreme events. There's no place in the world that has sufficient mental health counseling. And when they do have these events, and I know you've reported on some of our extreme events, I also think in terms of like school shooting, you have these big events and then a mental health professional will come in for 2 days. And the consequences go on for years. And so thinking about the long-term mental health consequences is an area that there's quite a bit of research being funded at the moment. Oops. Oh, that's good. It didn't go too far. Heat. As I said, most of the research has been done on heat. When we think about heat, what we need to think about is the core body temperature. Our core body temperature needs to stay within a pretty narrow range to protect our cells and our organs. So this is not the temperature you measure with a thermometer. And because it's our core body temperature, people are not very aware of the core body temperature. It's not easy for anyone to tell if their core body temperature is rising. A challenge with heat, and a place where you can really help, is a natural part of the aging process. As people get less well able to tell, they're getting into trouble with the heat. So we're not starting at a really great baseline, and then it gets worse. And so finding ways to communicate to people that they don't think they're at risk is a persistent challenge. Anyway, our core body temperature integrates our experiences throughout the day. I was up at the gym this morning because people are working out very aggressively, and their core body temperature is rising while they're working out. Then they're going to go and they're going to shower and they're going to go have breakfast, and their core body temperature is going to go down. And we have experiences throughout the day. Our core body temperature goes up, our core body temperature goes down, and it's kind of an integrating function over time. We know from the hundreds of studies that have been done on heat waves that when you have a heat wave, mortality starts in about 24 hours. It tells you that the core body temperature is integrating experiences over about 24 hours. And so it's not instantaneous exposure to heat that kills, it's the hours of exposure to heat. It's that core body temperature rising. We have behavioral and physiological mechanisms to keep our core body temperature in the normal range. Behaviorally, clothing. When it's hot, people go find someplace cool. Go find shade, go find a body of water. There's all kinds of things we do to try and cool down. Physiologically, our body responds to these higher temperatures in a range of ways, including sweating. And when those are insufficient, then our core body temperature rises. When it gets to the point where it's affecting our cells and our organs is when you start seeing hospitalizations, you start seeing mortality. We know from excess death studies that about half of all deaths from a heat wave are cardiovascular. And this means the heart is particularly sensitive to being heated. But for some people, it's kidneys. There is a syndrome, chronic kidney disease of unknown origin, that is prevalent in parts of Mesoamerica, Sri Lanka, and India. It's outdoor workers. There's multiple factors likely contributing to this. Heat makes it worse. And so you can see different organs being affected when there is exposure to high temperatures. Sort of a long explanation of that. We know that exposure to heat is rising. Data from the Lancet Countdown from 1980 to current. Adults over the age of 65, children under the age of 1, both groups are particularly susceptible. Exposures are going up. These are not the only susceptible groups. I mentioned pregnant women. There's a paper just came out about medications that I mentioned. There's more being understood about the wide range of susceptible groups to heat. There's quite a bit of work in agriculture, not so much in health, looking at outdoor workers. And there's a relatively new metric or capacity for particularly focused on agriculture. Because as it gets hot, as we all know, when we're too hot, we don't really want to work as hard as we normally do. And so there's lots of concern from the agricultural sector about what's going to happen with worker productivity with higher temperatures. This is relatively complicated, but it's different time slices. The left is the growing season. The right is the hottest period of the year. And the question is, how much could worker capacity decline with higher temperatures? So where you see the red colors, you're seeing quite large declines in the capacity of outdoor workers to work. You'll see papers coming out about this. This has not been covered as much as the health papers, but obviously this is critically important for industry, for agriculture, for any place where you see outdoor work. And also thinking about places like the Middle East, where already they do much of their construction work at night because it's just too hot during the day. I also wanted to mention something that has arisen a few times in the media where there is some confusion. There is a range of studies about survivability in the future to high temperatures. Nearly all of these studies have come from climatologists. The papers generally did not include anybody from health and did not include a physiologist. And some of these papers talk about livability, some of them talk about survivability. And so Jenny Vanoss at ASU led this paper involving physiologists to make sure that it was clear what are we talking about when we talk about survivability and livability. So survivability is a recognition that at some combination of temperature and humidity, it's too hot. Our core body temperature rises and people die from heat stroke, right? And people do die from heat stroke. That's a survivability question, and you can see the definition is the core body temperature exceeds 43 degrees C for a 3 or 6 hour time window. But sadly, you do see occasionally professional athletes dying from heat stroke, which goes back to it's not easy to tell when you're getting into trouble with the heat. If professional athletes can't figure it out and the people around them can't figure it out, it gives you a sense of how challenging it is. Livability is different. Livability recognizes humans live in all kinds of environments that seem improbable. People live in Antarctica. People live in the middle of deserts. We've managed as a species to live all kinds of places. And so the question with livability is, can you have activity without having positive heat storage? Are there conditions where you can still live there? It's going to be hot, but you can live there. You might not work very hard. The heat may make it more difficult. But thinking about these as two different concepts, because they are different concepts, and they're understood by human thermal physiology. And I put this in because another debate that you've been seeing is about temperature and humidity, which we can talk about later if you want. But these are for different groups. On the left are adults 18 to 40, on the right, adults over the age of 65, and then there's outdoor sun exposure, indoor shaded exposure. And the survivability limits are these black lines. And so this is a combination of temperature and relative humidity, and without going into this in any detail, you can see they all look different. And that's the other thing that's important when you look at these studies is the survivability limits are different in different age groups. A factor in, this thing's having trouble, a critical factor in the thermal physiology is how physically fit people are. So physically fit people do better under more extreme conditions than people who are not physically fit. And so when you see these papers on survivability and livability, first of all, make sure that the paper is clear on what it's actually talking about, and understand there's a lot of nuance here. It depends on people's activities, it depends on their clothing, it depends on the infrastructure. I hope that was relatively clear-ish. Come back to me later if it's not. I've been talking about some issues singly, and I'll continue to talk about issues singly because that's where the literature is. This lovely graphic from Luke Kemp just really emphasizes all of these things occur together. And that's one of the challenges. I put on the right some on wildfire smoke exposure because I live in the West. When it's hot, we worry about wildfires, and they come together. And so studying these individually is traditionally how issues are approached in health, but we have to put these together. Another point I wanted to make on wildfires is that the way we measure air quality is about particle size. So it's PM, particulate matter, and it's about the particular size of the particle. And there's a size of the particle, PM 2.5, and when you inhale PM 2.5, it goes deep into your lungs. It can stick to your lung tissue and be absorbed into your body. Particle sizes larger than that, you inhale and they get stuck in your bronchial tubes. Smaller particles, you inhale and exhale. They just come in and out with the air. So there's this one particle size that's important. And this is measured as a particle size, not what the particle is. And almost all of the studies on PM are on what comes out of our tailpipes. Wildfire smoke is different. It's not just trees, it's houses, it's cars, it's petroleum stations, it's all kinds of things that burn. But just what's being measured is the particle size. The toxicology studies are coming out that wildfire smoke is about 3 times more toxic than what comes out of a tailpipe. So when reporting measurements about air quality, in the US we use the air quality index, keep in mind that it may say that it's somewhat hazardous, but you need to multiply that by 3. We had wildfire smoke coming into Seattle a few years ago, and using purple air in my neighborhood, the exposures in my neighborhood were about 250. Anything over 60 is unhealthy for everybody to breathe. There's not a lot of research about what happens when people have these short-term, very high exposures. There were some wildfires a couple summers ago in California. One neighborhood had air quality readings in the 750s. And understanding what that means then for developing lungs is a place where there's going to be research coming out. Moving on to vector-borne diseases, always an area that people have a lot of interest in. I'm not going to go through this slide. It just makes the fundamental point that temperature, precipitation affect the development, survival, and reproduction of vectors, and vectors are mosquitoes and ticks that can transmit disease. Separately, temperature can affect the replication of the pathogen in the vector. So the modeling here is more complicated because there's an interaction between these two. And understanding that requires some pretty sophisticated modeling. And there's lots of really good modeling coming out of this. How many of you have reported on dengue fever? Not many. For those of you who don't know, dengue fever is raging in the Americas, around the world. This is the last year. These are the notification rates per 100,000. The darker red are places with much higher numbers of cases, which is pretty dramatic in how many places reporting higher dengue fever. It's particularly bad in the Americas. So this is the situation of the end of October. Last year, there were about 4 million cases total reported. We're over 12. 200% increase. In February, Brazil was very concerned about dengue fever. It always has a high number of cases. It came out in February that it expected that there would be about 4 million cases in Brazil of dengue fever. That's twice what was expected last year. I think I'm cutting out.
So, yes, ma'am, I apologize for the inconvenience.
Not your problem. Great. Brazil's had something like 9 million cases. And you can see, this is across this year. This is the 5-year average. That's last year, which was quite a record, and this is today. There was a detection and attribution study done. It's in a preprint, it's available online, that says about 40% of dengue fever cases in countries like Brazil are because of climate change. The mosquito that carries us in the Americas is Aedes aegypti. It's changing its geographic range. It's changing its seasonality. So those cases are being reported earlier and later than before. And when the temperatures are warmer, there's more mosquitoes. You increase the intensity of transmission. And as you can see, states of emergency were declared in Central and South America because of the number of cases. This is going to be repeated, unfortunately, in other places as we go forward, as this mosquito continues to change its geographic range and temperatures continue to go up. Another example, which is a little more complicated than dengue, is Lyme disease. Lyme disease is carried by a tick. It has a quite complicated 2-year life cycle that I decided not to show you. When you think about how climate change could affect Lyme disease, because it's more complicated, when you look at the studies, and it's true both for mosquitoes and it is for ticks, a lot of the studies are done on the distribution and the abundance of the mosquito. Because if you have surveillance, and that's a pretty big if you have surveillance, it's easier to determine where you've got the mosquito. But then you've got to determine when the pathogen gets introduced into the mosquito or into the tick. And that's harder. And so first you need to have the mosquito or the tick, and then you need the pathogen being introduced, and then you can start have transmission. Whether you have cases depends on the status of your health system. Do you have access to health care? Are they testing for it? An issue in Canada has been that Lyme disease didn't used to exist in Canada. And so there hasn't been testing until recently for Lyme disease in Canada. So some people would travel to the US to get diagnosed because they couldn't get diagnosed in Canada. And so it's not just that something appears overnight in a new location, it's a multi-step process. There's quite good surveillance in Canada on Lyme disease. And I'll just show you. This is in part of Ontario over just 6 years, and these are actual cases of Lyme disease. And you can see, starting in 2010, going down to 2016, just how rapidly the numbers of cases increased. And this means behind this, of course, was the tick became established, and then the pathogen got introduced, and then you started having transmission. So these kinds of patterns are going to be repeated in other places. The problem is we don't have great surveillance. For those of you who don't know, in the US, surveillance is a state-level activity, and with everything in the US, if it's a state-level activity, there's variability from state to state. Projections. So these are classic projections of what could happen under different scenarios of greenhouse gas emissions. This is the iconic figure from the latest IPCC report. It's for heat waves, 1 in 10-year events, 1 in 50-year events. This is closest to me, so I'll do this. So once in 10 years was established in the period 1850 to 1900, and then looking today and out into the future under different scenarios of how common. I've used this many times in my talks. I usually focus on the 1 in 50-year events. And this is unintentionally, this is misleading because it gives the impression the extreme events are 1 in 50-year events. The heat dome was a 1 in 150-year event. There was an event in Sweden where the Swedish Meteorological and Hydrological Institute estimated the return period, how often you'd see that heat wave, was 1 in every 3 million years, which I can't even begin to conceptualize. There has been events in Japan that were virtually impossible without climate change. And so this 1 in 50-year event is going to be incredibly common if, unfortunately, we go as high as 4 degrees C by the end of the century. And so going back to that picture of the cohort effect, the number of heat waves we're all going to be exposed to is going to increase significantly depending on greenhouse gas emissions. When we think about what could happen in the future, I made the point we're talking about risk. And this is one of 2 slides I have that emphasizes the importance of adaptation and mitigation. These are projections, heat-related deaths, end of the century, obviously in the US. And if you compare the upper left, where there's no adaptation and high emissions, the bottom right, adaptation and low emissions, those are different worlds, completely different worlds. And you can see the difference between when you have just change in mitigation, just change in adaptation. The other point is that when you look at the bottom right, even in that world with adaptation and mitigation, there's increases in heat-related mortality. Populations are aging. We've got more people at risk. And so there's going to be a greater burden on our health systems, even with adaptation and mitigation, because of other changes that are going on. Projections for vector-borne diseases, obviously the United States, looking at Aedes aegypti. Aedes aegypti can carry dengue fever, chikungunya, and Zika. Also can carry yellow fever. This shows the projection for climate suitability for the mosquito, right? And so the buff kind of area is where we are likely having the mosquito today, where it likely exists today. Again, we don't have great vector surveillance in all of these states, so that's not clear. It's a modeling study. And projecting towards the end of the century under high greenhouse gas emissions is the red area. So it shows that the environment for this particular mosquito will change dramatically over the course of the century, including possibility for Seattle up there to see Aedes aegypti. But it's not just whether the mosquito's there, as I explained with Lyme, it's when do you have a summer that's hot enough and long enough that if you introduce, in this case, dengue fever, you could see transmission. And that's what the bottom one on the right says. And so much constrained range for where you could actually have transmission. We do know we get dengue in Florida, other southern states. We get dengue in parts of Texas. And that with further warming, we could see transmission in a greater area. This was published about 2016. And a couple of years after that, breeding colonies of Aedes aegypti were found in Toronto, Toledo, and Detroit. The mosquito can breed in the water in the bottom of a flower pot. I've never done this. I know entomologists who've done this. If you go into sewer systems, there's millions of mosquitoes. It's warm, it's moist, there's places to lay their eggs. We put grates in the sidewalk so the females can come out and get a blood meal so they can lay their eggs. We have a perfect environment. And once you have breeding colonies, it's almost impossible to get rid of these, which means that in many areas, health is just like other parts of climate science. We're under-projecting the risk. If we've already got established colonies outside of this range, then the question is when transmission could occur, not if. Yeah.
This study uses RCP 8.5. Can you just speak to the fact that people have sort of ceased using that scenario so much in their work?
All right, so I'm going to pull out my big soapbox and get on top of it. The representative concentration pathways, there's 4 of them, are different pathways of greenhouse gas emissions into the future. And based on those projections, the climate models are run and they do changes in global mean surface temperature out into the future. Each climate model is based on first principles of how our climate system works. So it has what goes on in the atmosphere, the ocean, the land, the cryosphere. And so each model is different. There was a model that was used in the first US National Assessment. I think it was the first US National Assessment. It has 1 million lines of code. These are incredibly complicated models. And every climate model is a little bit different. So when you look at the IPCC report and they do projections, they show you these big cones of the range of projections from the climate models, because they're all a little bit different and they initialize a little bit differently. And that's important to understand because although RCP 8.5 is based on emissions that are no longer consistent with where we are today, the projections from 8.5 overlap RCP 6. And so it becomes a communication question of, should we start having variations on RCP 6 where we have very high levels of warming? Or do we just keep using 8.5 because it gives you that high level of warming and you want to look at the range of uncertainties? And so there's quite a few people in climate science who say we shouldn't use 8.5 because the emissions are wrong, but the temperature projections are still the same as what you'd see under a lower rate of emissions. And there's choices here to be made on how to best communicate that, and mostly the choice has been to just keep using 8.5 because you get that high rate of warming, knowing you could get it under 6, then try to explain to a decision maker. We know how well decision makers handle the ranges of uncertainty. Some of them are great at it. I think the biggest health risk in a changing climate is going to be food security, and that comes through 2 mechanisms. The first is how temperature is affecting crop yields. This is maize or corn, rice. I'm not going to talk about soybeans because they are completely different, and then wheat. Mid-century, end of the century, different colors, different greenhouse gas emissions, and you just look at the patterns. Right? That crop yields are falling in parts of the world that are the most vulnerable. So that's ongoing, and that's just going to continue to become worse, unfortunately. The other is through carbon dioxide itself. So this is not climate change, this is carbon dioxide. All of our plants use a photosynthetic pathway to bring in carbon dioxide from the atmosphere, bring it into the plant, and break it into carbon and oxygen, and use the carbon to grow. There are just a few major photosynthetic pathways. 85% of our plants use one photosynthetic pathway. That's barley, wheat, rice, potatoes, grasses, trees, 85% of what you see. The biochemical characteristics of that pathway means that these are called C3 plants. That's all that it means. C3 just means it's a particular photosynthetic pathway. There's been field experiments for wheat and rice, where you've got a big field of wheat or rice, you divide it into plots and blow carbon dioxide on some, you don't blow it on the others. And these are concentrations expected later this century. And under those experiments, protein declines 10%, B vitamins decline about 30%, and then through a different mechanism, micronutrients decline about 5%. The nutrient density of our food is declining. Estimates of how many people could be affected range up to the hundreds of millions of people being affected by this. There's about 830 million people, 630 million people in the world are food insecure. There's over 2 billion that have got micronutrient deficiencies. About 1.5 billion women and girls have iron deficiency anemia. That 5% reduction is going to put many more into those categories, which will have just profound effects for health and well-being. So this, from my perspective, is just really important. There's been some research in this area, not a lot. It's complicated. And the agencies that fund this kind of agricultural research, frankly, don't know how to get their hands around it, of what can be done to better understand and start thinking about what options do we have to be able to address this. I'm running out of time because I'm talking too much. Do you want me to talk about the burning embers, or this will take me like 3 minutes? Go for it. And then I'll skip to something on mitigation. How many of you have looked at the burning embers? Not many. So this goes back to the United Nations Framework Convention on Climate Change. Article 2 of the convention says the ultimate purpose of the convention is to prevent dangerous anthropogenic interference with the climate system. All the world governments negotiated that language and then signed off on that language. The negotiators then turned to the IPCC and said, we've all agreed we have to prevent dangerous anthropogenic interference with the climate system. How do you define dangerous? How many people skydive? We all have a range of internal what's dangerous, what isn't. And so starting in the third assessment report, there was an effort to understand what dangerous means. Came up with a rubric called Reasons for Concern, and it's reasons for concern for dangerous anthropogenic interference with the climate system, and then did a complete literature review to say, what do we know? And use the color scheme you see here. In this color scheme where it's white, it means that scientifically it's not possible to tell if there's been a change in a system. If it turns to gold, it means that there has been a change in the system, and at least some of that change is because of climate change. When the color turns to red, the risk is high. When it turns to purple, the risk is very high. These are burning embers for health. They're called burning embers because of the color scheme. So the 0 is pre-industrial temperatures, the y-axis, increase in temperature above pre-industrial. There's only 6 that have been done for health, but here's the one for heat. The program we use to generate these puts these enormous dots on here, and that just gives you the level of confidence in the transition. Scientifically, what we're asking is, where do you transition from one level of risk to another? So what we did differently in health is we have not just one set, but we've got 3 sets for each of these because there are 3 different visions of adaptation. There's limited, incomplete, and proactive adaptation. And just like the figure I showed you for heat, you can see how important both adaptation and mitigation are. You have to do both. When these went through the approval process for the Working Group 2 report, took us, I think, 8 or 9 hours to get the figures through. The major comment from all of the negotiators was, why aren't there more? And so these are going to become more common. You're going to see these in more places. And I'm happy to answer more questions on these, but I think it's really useful to understand, because once you've explained the rubric, everybody can interpret these. You can just see how the risks are shifting with different temperatures and how much you can do in terms of adaptation. Let's see if I can make this. Adaptation, tons of effective adaptation options. We can get to that later. Major constraint, limited investment. Heat wave early warning systems, we'll skip that. Lots you can do to protect yourself during the heat. Infographics from the Lancet. Tree cover is important. There's been, of course, all kinds of declarations in this last year. This was from the COP, and then I have one from the last World Health Assembly, doing a lot more about climate change and health. So this is the scariest slide I have, and this shows greenhouse gas emissions, showing, frankly, not much has changed the trajectory of greenhouse gas emissions. All right, come on. And then I'm gonna just do two more slides, 3 slides quickly. A message that hasn't come out very clearly, despite efforts in the health sector, is when you look at the different policies and technologies to reduce greenhouse gas emissions, they all have health benefits. And when you look at these health benefits, it's possible to quantify the avoided hospitalizations from closing down coal-fired power plants. It's possible to quantify the number of avoided premature deaths. Economists like to value things. And so economists will value these avoided hospitalizations, the avoided premature deaths. And the summary across all the research that's been done is the value of the health benefits is of the same order of magnitude, if not larger, than the cost of mitigation. We should be mitigating for our health. It will pay our societies back in better health, in longer lives, and the benefits are today. And so the focus really needs to be on focusing on the health benefits, not just how much it's going to cost. And there's lots of research to support any of that reporting. I put this in because I love the photograph. And this is one of many examples. It's from New Zealand, just doing a full kind of life cycle assessment of what if we get 5% more people on bicycles. And you can see $200 million in health costs saved. Pathfinder Initiative, if you haven't looked at it, is a great resource to talk about some of the ways to reduce greenhouse gas emissions. And then I wanted to end with, when we look at climate change and health, about 85% of the health risks are in children. So in the US, you say climate change, people still think about polar bears. So I spent a lot of time trying to have people think about what it means for children, because the children are the ones who are being affected today and will be affected in the future. Thank you.
Thank you for a thorough and sobering summary. So we're going to take questions. Please wait for Roz to bring you the mic so that it can be heard over the recording. Please give us your name, affiliation. Take your turn with one brief question. If you have a longer discussion topic or comment, Chris is around all day for that.
Thank you so much for a great presentation. It was so great to see you at the gym this morning. My name is Miriam Vidal. I am a freelance journalist. I'm from Mexico, US. One of the things that I started, wondering when they sent us the survey so we can try to find what to work on today, and I was trying to look for correlations, between disease and climate change. One of the things that was problematic for me is that there's no data. There's a lot of correlation, not causation. So I guess my question is, how can we as journalists make attributions? Usually what we do is we look for papers, we look for scientists, and the scientists are the ones who are finding the attributions. If we want to do the same thing, how can we do it? How can we say, yes, it's climate and this is impacting this? No,
it's a great question. Can you go back to the second slide? It'd be easier if you do that than I try to flip back. the gold standard's detection and attribution. I think the world literature on detection, attribution, and health right now is about 15 papers. So small, but the number is going to dramatically increase. But if you go back one more, so looking at these, as I said, much of the literature has been done on heat. We have a strength of association. We know the association. There's consistency. It's specific. We know the exposure comes before the outcome. And so it's useful to look at these criteria, and you can just go to Wikipedia and pull off a description of all of these. Because in some places that we've got that. Other issues, leishmaniasis, there's some papers, not a lot of papers, and aren't quite there yet. And this is why I think it's quite important to understand the etiology. Because if you have the etiology of the disease, with leishmaniasis, we know it's carried by the sandfly, we know the sandfly is sensitive to temperature, and so you can start making that causal chain of saying, even though all the evidence isn't in, it's plausible that there is attribution. There's others where it's more difficult. There's been a whole series of papers just correlating temperature with a bunch of accidents, but they don't really have the etiology described, and it's a little hard to understand why that would be the case. And so this is more a sense of thinking through, is the story solid from the perspective of causality? Yeah?
Virginia Kewen, I'm a freelancer from Portland. And so I just wanted to ask, to what degree are you can you say the quantifying the health benefits is having an impact with policymakers? Is that something that is resounding, and especially, facing our future policymakers of the next 4 years? Like, what is a good example of the best way to make this case?
You mean on the health co-benefits? There's been very little inroads with policymakers on this story. And it's one of the reasons I hope you all will carry it, because policymakers read the media, they don't look at the scientific literature for obvious reasons. But there are discussions with policymakers who are now trying to bring this on board. So there's more uptake of this in Europe than there is in other parts of the world. But efforts are underway. The Pathfinder initiative is getting a lot of attention, which is great. It's got examples of effective mitigation policies going into, mitigation of greenhouse gas emissions going into policies. And so Pathfinder initiative is now in phase 2, just starting phase 2 and looking for more examples and partnering with like C40 and others. So that it's starting to come out, and with all the attention on the Pathfinders, we really hope that there will be greater uptake of this by policymakers.
Hello, my name is Patrick Aftor-Arsagas. I'm with the AP. I'm a Sure Fellow as well. I was just curious your thoughts on, I feel like heat I'm a visual journalist, and heat is a really challenging thing to cover because you can't see it. But it's incredibly impactful. So I'm just curious, any thoughts that you have about how us, particularly as journalists, could cover it in a way that gets people to care about it outside of these extreme events that we have?
Yeah, it's a good question, and I feel how difficult it is. There's been a number of photographs that I think have been impactful. Massive heat waves in India this year, and there were photographs of hospitals with separate rooms set up for heat stroke patients. So a big sign outside, if you've got heat stroke, you go here. And those kinds of pictures can really help. The other thing I thought was really interesting is when Sweden first put in its early warning system, there was a website, of course, that you could go to. And they put photographs of dogs on it because people stop and look at pictures of animals. And so they were getting people to stop and look at these really cute dogs on the beach. And then, by the way, it's really hot outside, to see if that would help get people to take the information up better. I think we need to think more broadly of how better to communicate. I think there's so many opportunities we're not yet capitalizing on with heat wave early warning systems, thinking about involving faith-based organizations, think about trying to reach out to pharmacists. They know every prescription drug everybody takes, and they know which ones affect the ability of your body to sweat. And so thinking about different kinds of ways to reach out to people to have a better sense of the challenges we have in communicating around heat. And again, people just can't tell they're getting into trouble with heat, and it becomes, I was in an event and the person in front of me collapsed from the heat, and nobody around the person had any idea. There was medical care about 40 seconds away, so it was all good, but it's just such a difficult issue to try and communicate. Yeah. And thank you for what you do.
Christian von Preissing with KRGV in South Texas. Do you think some states, municipalities are not doing as much as others in terms of documenting heat illness and heat death so that we have the data available to understand the trends?
So first of all, heat deaths is hard. And there's nowhere that's capturing the total number of heat deaths. And that is, if you go back to 1995, when the first big heat wave captured the attention of the scientific community and the media, was in Chicago. And there were statements about how many people died, and only afterwards was there an effort to calculate the number of excess deaths. I keep mentioning this because that's the only way you're going to know. And when you think about it, because heat exacerbates so many other conditions, think about it from the perspective of an emergency department. 2 people come in having a heart attack. The goal of the emergency department is to save those lives. But how to tell if one was exacerbated by the heat but one wasn't? It's really very difficult. And you don't want to take the time away from the people trying to save the life to figure out how much heat contributed to it. So there's been efforts to try and increase the reporting around heat-related mortality, but there's just fundamental challenges with that to be able to figure it out. Heat stroke you can do, but all the other health outcomes are pretty challenging. Instead of thinking about increasing the reporting, more accurate reporting on a death certificate, in France, after the big heat wave in 2003, where there were 70,000 excess deaths, they changed their surveillance system, and it's not real time, but within a very short period of time, they know how many people are dying, because they didn't know in 2003. Same thing in British Columbia. They now have very rapid reporting of their death certificates. So they can run these analyses pretty quickly to get a sense of what's going on. You can think about different ways of reaching out to funeral parlors and other places to try and get a sense. But that end is going to be more effective in getting more rapid understanding than putting an additional burden on people in hospitals where I just keep emphasizing it's really hard because you see an increase in cancer deaths. Well, how do you know which ones were increased by heat? And when we do these analyses, we do them at the population level, and so we can give you the numbers at the population level, but it's not at the level of the individual, because that would require a deep understanding of their physiology, their risk factors, what their exposures were for the last 24 hours. And there are places that do that kind of social autopsy afterwards. It's very intensive and takes a lot of work. I think getting better reporting and more fast reporting will get us further ahead faster. And it'll be beneficial for other issues as well.
Hi, my name is Anna. I'm based in Houston with Univision 45. And I was wondering about the attribution studies, because recently we're always listening, okay, so this was attributed to climate change because of this. And I've seen the Climate Central work. I've seen the world attribution
world
work
weather
too.
Yeah.
But also I can tell that there's a lot of doubts about, okay, so how can they do this so fast and so quickly? So I guess my question is, in what parts should we as journalists probably be paying more attention to because especially with in Valencia with the Dana, I was with a friend and we started searching, okay, so what was the difference between one race and another's with the time? And there was not a big difference, you know? And then there was another factor, and is that all the bad urbanistic development that has been going on. So how can we actually tell, okay, this is attributed to climate change?
There's a bunch of answers implied in those questions. So the first is, on the health side, there's casual use of the term attributed to without actually doing the attribution. On the climate side, there's sophisticated methods that are used to determine the attribution. And this is attribution to the hazard. It's not the impact attribution. And so what most of the impact sectors are doing is a two-stage detection and attribution, where you have the detection and attribution on the hazard. And then on the impact side, you've got the detection of whether there's been a change, and then you use the attribution from the climate science to do the final attribution of the impact. There's rapid advances in methods, but it's just having the core understanding that there are recognized methods to do this. They're hard, right? The detection and attribution study for the Pacific Heat Dome is published on world weather attribution, and it's a team of like 25 people. And that was really difficult to attribute. It wasn't difficult to attribute. To come up with the precise attribution was difficult because the event was outside the climate models. And so what they typically do is look at the climate model runs, look at the extremes, look at how frequent those extremes are, and then come up with to what extent did climate change increase this. But the Pacific Heat Dome was such a huge outlier, they couldn't get the climate models to replicate it, which says something about what needs to be done for climate models going into the future, where we're having these really extreme extremes. But yes, those methods are all worked out. They're all peer-reviewed. The math is complicated. I will not pretend I can try and explain it, but they know how to do it. And if you need a reference, you can go to the chapter. I think it was led by Freddie Otto in the IPCC Working Group 1 report that lays that out. And then on world weather attribution, they've also laid there's references there to the methods that have been peer-reviewed, and you can have access to those as well. And good luck with the math.
All right, we're going to take a quick break. I want to make sure everybody has time.